Okay, so this is the quiz you took yesterday for most of you and today for first block. And let's go over it and let's see, and let's move on with solutions. Somebody's asked me to go ahead and give you video on the solutions PowerPoint that we're going over in class and that your test is on Thursday for. So if an atom contains 3 protons, question number 1, and 4 neutrons, and 3 electrons, what is its mass number? Now, by this point, you should know what mass number is, and that's the protons plus the neutrons, so that's protons plus the neutrons. People have circled, as you see here in this example, they've circled A. A is wrong. A is the number of electrons, right? Number of electrons has nothing to do with mass. Remember, we went through that whole a whole day on this and a couple days reviewing and looking at questions. You've taken quizzes and tests on this, so my only guess is that you've forgotten about it if you got questions 1 and 2 wrong. However, what worries me is that by the end of this year, you'll have to remember a lot of this stuff, and if you're forgetting it in a month, there's an issue. All right, we need to do the 6 R's. We need to review every day. You need to keep it fresh in your mind. Every day that goes by that you don't keep it fresh is information loss, as you can see here with this question. So if an atom contains 11 protons and 12 neutrons, what's its atomic number? By now you should know its atomic number is the number of protons. So the answer is B, and this person here chose 23. This was a predicted answer. That the question was, would they remember that the proton number was the atomic number? And if you got this one wrong, my guess is that's why you're getting all the other questions wrong, because if you didn't understand this, and all of you got it right on your assessments when we covered it, you just had forgotten it or you're not applying it. And that's the atomic number is the number of protons. And if you don't remember that, you couldn't answer half the questions on all the quizzes since, which explains why you were doing so badly on those quizzes. So if you're not getting this, I don't know what to say. You have to go back to the drawing board. 23 was a predicted answer. That's the mass number. So this is the mass number. I've seen some people choose 1, choose 12. If you've chosen A or C, C, I guess you might think the atomic number is a neutron number, but I think at that point you're guessing, and number 1 is just way off. There's no reason to choose A. All right, moving on. Water molecules are polar with, at this point, all the rest of these are wrong. Oxygen side being slightly positive, that's wrong. Everybody should be able to. We've drawn it over and over again. You had several quizzes on it. We've gone over it, over the quizzes. I've made movies about water. We've had videos in class about water. We've talked about water. We've drawn it on the board. I don't know what else to say. This is partially positive. These are the hydrogens. They're partially positive, and this is partially negative. This is like Mickey Mouse, where let me redraw that in red. This is like Mickey Mouse, where you have your oxygen is partially negative. The picture diagram looks like Mickey Mouse, and your oxygens, I'll do it in black, are partially positive, right? We've talked about this over and over again. This is because of the polar bond that's happening between hydrogen and oxygen, and it creates this dipole. This dipole moment. Why is this a dipole? Because you have 2 poles. You have a positive pole and a negative pole. Di means 2. All right. So in any case, water molecules are polar and the answer should have been oxygen being slightly negative and hydrogen being slightly positive. The answer should be D. Obviously, oxygen, hydrogen, both sides being partially negative, that's just wrong. And because of the drawing that I just told you, that I just drew here, I warned you should make the drawing. And you'll see the drawing. You can even see the drawing over here. So there's water, and you should, at this point, should be able to quickly say partially positive, and this is partially negative, and that's true for all of them. And that'll help. If you could do this right, then you would have gotten this answer right for sure, And we'll talk about what that means in a second. So if you were to do that, and you see all these negatives pointing towards the center here, that lets you know that this middle one is what? Let me write something that I've told you that you've all repeated like a mantra over and over again. Opposites attract. And so if these are all negative here, then the center one must be positive, right? Opposites attract. So that's no question. There should be no question about that. All right, so moving on to, and of course, the last one, oxygen and hydrogen, both sides being slightly positive, is again wrong for exactly what we just talked about. So really, there's only one answer here. And there's only one answer up here. It's not that one, or this one. The answer is 7. 4 plus 3 is 7. So that lets you know about 1, 2, and 3. And so this was wrong as well on this particular quiz. This is someone's answers, but hopefully they'll do better on the next few questions. What do cohesion, surface tension, and adhesion have in common with reference to water? So what do these three things, cohesion, surface tension, and adhesion? If you were paying attention at all to to what we discussed in class, to the video that I created or the video I sent you, any of those, and the video I sent you, I think is 15 minutes, and we even showed it in class, so there's absolutely no excuse. So these three things, what these three things have in common, they all have to, in reference to water, is that all of them are all properties related to hydrogen bonding. That is correct. The answer is C. So all increase when temperature increases, that's just not true. All are produced by ionic bonding. We know that's not true. It's due to polar bonding. Polar, or what we call dipole-dipole forces, and we'll see that in a minute. All have to do with nonpolar covalent bonds. Obviously not, because water is polar. We drew it. Has two sides. In fact, it has a dipole, 2 poles. And C and D can't be true because this is nonpolar. This is nonpolar, which means this would not have any partial charges, which is obviously not true. Why does ice float in liquid water? This is the answer that was predicted. This is the answer a lot of people chose. This is wrong. And the reason most people chose it, or a lot of people chose it, not most people, but a lot of people chose it because they saw this crystalline lattice. And the crystalline lattice is what's created when the molecules are in its most stable form, when they're stabilized. But, so that part was right. Of ice, that's all is correct. That's what happens when you form ice. It creates a crystalline lattice. And people remembered that like a word search game that they used to, homework and quizzes that they did in middle school, and they remembered it from the notes, and so they circled it. And they were done. But they didn't read the rest of it. And it says it causes it to be denser than a liquid. And almost everybody on the other assessments, on the in-class assessments, the questions I asked, and the questions on the quizzes, everybody knew that dense means things sink, not float. And they're asking you, why does ice float? It's not because it's denser than liquid water. That's not true. And also, if you watch the video in class that I showed you from online, from the South African professor, if you listen to what I said in class and took notes and studied the notes, if you watch the water video that I sent you that took me about an hour to get it done, any of these, if you read the book, the chapters on water and these bonding events, then you would know that this is not true. Any one of those, if you've done any of those, not all of them, if you've done any of them, any one would have got you this answer, would let you know that this answer is wrong. So so if we look at D is the actual answer. It says hydrogen bonds stabilize and keep molecules in ice further apart. That's that crystal lattice. That's the definition of crystal lattice, right? And for water, all right? And molecules, then the molecules of liquid water. That is D. So this is wrong. Ionic bonds between molecules of ice, there's no ionic bonds, right, between the molecules of ice. So no one should have chosen this, but I'm sure someone did. If you chose it, you just didn't understand what was going on. Liquid water molecules have more kinetic energy than supporting them than ice. Well, that's true, but it doesn't explain why it floats. That's not the explanation why it floats. It floats because it's less dense, and it's less dense because the hydrogen bonds stabilize the molecules and they keep the molecules further apart, which makes them less dense. Ice always has air bubbles, although they always have air bubbles or usually have air bubbles. Ice, those air bubbles really are not what's making it less dense. And not always do you have air bubbles. Ice for frozen water, solid water, is less dense than liquid water. I mean, that was the point of the last week. So if you didn't get this one right, number 5, you're not reading the question correctly, or you really haven't been studying. It's up to you what the answer is. Based on your knowledge of the polarity of water molecules, the solute molecules most likely, and I told you in class, you wrote it down, solute's the least amount. Which one is the least amount? It's this one in the center. Obviously, these 5 look different than this one. Based on your knowledge of water, what is the knowledge of water I'm talking about? Positives on this side, negative on that side. Positives on this side, negative on that side. The one in the center, knowing that opposites attract, the one in the center must be positive. So the answer is positively charged. So this person got it right. Positively charged. The unique attractive forces that keep water molecules together, and I warned you, I said choose all that apply. That means there's more than one answer. That doesn't mean they're all right. So strong forces are nuclear forces. We talked about a long time ago. And what happened here, I'm sure this is, again, another example of people kind of remembering what's going on. They remember me going over strong and weak forces in the beginning of the quarter. They just weren't sure what the heck was going on. But they forgot, in this case, what we've been talking about for the last week, which is water has these forces that pull them together. Again, in all those resources I spoke about earlier, we talked about adhesion, cohesion, hydrogen bonds, and hydrogen bonds are the reason you have adhesion and cohesion. So C is correct, right? And D is correct. So cohesion is when water molecules stick together. Water molecules attracted to water molecules. So, and the only reason I would say maybe someone might choose C on its own if it was a sophisticated answer, which is to say that the word unique might tell you that we're talking about hydrogen bonds, because hydrogen bonds are somewhat unique to water, although they do occur in DNA, and DNA is not water. So I would argue that these two are the correct answer. So this one's wrong. The property of water whereby molecules tend to stick to one another is called property of water whereby molecules stick to one another is called cohesion. That's correct. Now see, there's where I have a problem with someone choosing hydrogen bonds up here, because it says unique attractive that keep molecules of water together. And then in the very next question, water molecules stick to one another. Why would you not choose cohesion as your second answer? Why strong force, something that you probably just weakly remember from the earlier part of the year? Oh, well, that's just the way it goes. So cohesion is the correct answer for 8. 9, the property of water whereby molecules tend to stick to objects is called adhesion. So that's correct. And water is unique because it is a solid phase. It is less dense than water. I can't tell you how many people did this. This person chose less dense than water here, but then chose more dense than water over here. So what does that tell you? This person didn't read this answer completely. This person read the first part of the answer and then chose. They didn't read the whole part, the whole question. They didn't think about it. If they had, they couldn't possibly choose less dense over here and denser over here. This is a mistake. This is a mistake of not checking your answers. This is a mistake of letting nerves get to you. This is a mistake of not thinking, not reading every answer completely. And yes, you only had 10 minutes, so you had to get the easy ones right quickly, and then give more thought to questions like number 5 and perhaps even number 6. So if you did 30 seconds on all the rest, you could do a minute and a half or 2 minutes on each of these, right? That's how you have to handle these tests. At the end of the year, the end of course exam is going to be rough if you don't start developing these skills. All right, so let's go on and discuss this is 15 minutes. This is done. We're moving on to the next part of the video, which is going to be your PowerPoint. We're quickly going to review this stuff and let you know what's going to be concerning it. So solutions. All right, so what is this Tyndall effect exactly? Well, on the exam, I'm going to give you a solution. It's going to have this light beam going through it. Or it might give you a colloid and you'll have a light beam go through it. Now notice this is a light beam going through a colloid. You see how when the light gets through this solution, there's no dispersion of the light beams, right? There's no separation of the light beams. What you get is just this through the colloid, you have the widening of the beam. You see how you see dispersion? The light beam isn't going straight through, so it's fuzzy on the edges. Where through the solution, there's absolutely none of this dispersion of light. So light beams are invisible in a true solution, but beams is seen when it is passed through any colloidal suspension because its light is scattered by the colloidal size microdroplets. So the bigger particles in a colloid. Remember, size is a big issue with colloids versus solutions versus suspensions. You get this dispersion or this scattering of the beam, and so you see it. You see it here happening with a laser beam. You see it here happening with a projector beam. It happens with the sun through the solution that we call air coming through a colloidal solution, right? So whenever you have a mist or a fog or even some smokes, you have this scattering of the beams, just like you see here, scattering of light. When it goes through a suspension like muddy water, it disperses. You don't see a beam at all. It just seems like a big cloud of light. Okay, so remember, suspension is probably going to be the easiest one you're going to be able to identify because it's muddy, it's cloudy. So that's the Tyndall effect. And when you're looking at suspensions, you have to know these three because I'm going to give you a particular solution. I'll probably be shining a light through it, so you'll be able to use what we just talked about a second ago to help you to identify one piece of evidence as to why you think it's a solution, a colloid, or a suspension, whatever your choice is. And then you have to add these descriptors, right? So clumps of particles rather than having single atoms or small molecules, aggregates of small particles, so between 1 nanometer and 100 nanometers, that kind of thing. You'd have to tell me that a solution is transparent, clear, or could be colored if there's pigments in it, right? It never settles, where the colloids coagulate, and where movement in the suspension is by gravity, so it settles down to the bottom, where movement in solution is the molecular movement, and colloids are because of Brownian movement, the vibration of the molecules themselves move them around. So this was because of electronegativity or electromagnetic forces, where this one is just vibrations or kinetic energy. So there's the Tyndall effect described again in drawing, and here's some examples of solution of colloids and of suspensions. So solutions are homogeneous mixtures, and that's where I'm going to leave it for a second, and I'll come back in the middle of class, and I'll continue this in class, and when I'm done with the PowerPoint, I'll send the whole thing out to you. So water is, in fact, an insulator, and if it's pure water. So let's think about the fact that water, as an insulator. Very much like rubber, okay? It will not conduct electricity well if it's pure water. Now, again, as I said, don't go trying to prove that water doesn't conduct electricity and stick a radio in water or something like that while it's plugged in. Don't do that. Water will conduct electricity if there's any salt in it at all. So tap water has a lot of dissolved minerals and therefore has this combination of positive and negative charges. And these guys can conduct electricity really well in water. And one of the reasons is they're moving around constantly, and the electrical charge can move from one end to the other. So the mobility of the electrons is increased by the liquid form of the water, and the salt going from Na to Cl. The electrons can move freely through the liquid phase from one pole to the next. All right? Or in this case, the pole is here. So from one pole to the next. So the electricity flows. And you have something that has high conductivity. Now, that's because it's 100% of this salt, which is normally what? NaCl together. When you put it into the water, it becomes Na plus and Cl minus. So you have 100% dissociation. It breaks up 100% of the time. All right, so that's water. That's a polar substance, and water does not conduct electricity, but if you have ions, if you have the solution of water with ions in it, it does conduct electricity very well. So now what happens if not 100% of the stuff breaks up into ions? What if it breaks up only partially? So let's take a look. So here we have a weak electrolyte, in this case, so CH3COOH, as you see here, it seems really fancy, but it's actually just acetic acid, or as you know it, the active ingredient in vinegar. And acetic acid is very, you drink it, it's a food at low concentrations. And so, and someone asked about the order of the elements. Why does it say COOH instead of CO2? And that's for several reasons. And one thing, it tells you something about the structure. It tells you that CH3 there's 3 hydrogens on this end, and this is important. And it's connected to a carbon, right? And how many bonds does carbon have? Like how many bonds can carbon make? And the answer is 4. So it's 1, and then of course you have another one here, right? Right. So then it needs how many more? 2 more. So you have a double bond. Now this oxygen needed 2 bonds, and it did get it, right? So now there's 3, but you need 1 more. Well, here you have it, O and then H, right? So the fact that it says COOH, it tells you that you have this double bond to 1 oxygen and an OH group. Now this OH group is going to become very important next week. This OH group is sitting there, and that's what we call a base. We'll talk about it's a hydroxide. And when it's an ion in water, hydroxide OH, negative, it's a base. Or it's one of our measurements for a base. So let's go ahead and take a look, though, at this thing called vinegar or acetic acid. Right? It's C double bond OOH. And that's why we put a CH3COOH. So we know that one of the oxygens is bonded to the carbon, and then the other oxygen with a hydrogen attached is bonded to the carbon as well, as you see here. All right, so all that was really unnecessary, other than to try to explain what the letters mean. But there's this molecule. Really, what you need to know for the exam is that there's this molecule here that's not broken up, right? You see, is there any charge? Is there a negative or positive anywhere on this? The answer is no. There's no negative or positive anywhere on that. So the next question is, what about the other half of it? It has another half, doesn't it? And this is, if this is 1/2, and I'm just going to say a half, it may not be a half, but let's say it's a half. So there's a half there, and the other half is what? Well, if you notice, it's CH3 is still the same, right? These two are still the same. Then you have another C, maybe hard to see, might be hard to view because the blue line is in the way, but that's C, and then an O, and then an O. But there's no H attached to it. The chemical reaction occurred, and it lost its H. But the electron stayed with the oxygen because the oxygen is very strong. It's still highly electronegative. That's why it was polar to begin with, right? So this thing here has a negative charge, and this thing here has a positive charge. So what's this? What do we call these things? No, let's not worry about the fact that this is acetic acid. Let's ask ourselves, this is a molecule, right? A molecule with no charge is neutral. What do we call this thing here? This thing with the negative and a positive? Well, hopefully, most of you are saying ions. So these are ions. And so these ions are broken up in water naturally. They break apart. A chemical reaction occurs. It's energetically favorable. You have this dissociation of hydrogen from the main body of the compound. Again, the molecule was CH3. Let me draw it again. Carbon and double bond oxygen, and single bond oxygen and single bond hydrogen, because again, oxygen needs 2 electrons. And so what happens is these 2 electrons go with oxygen, and then this hydrogen goes away by itself, and what you end up with is CH3, and get used to it because we'll be doing a lot of this, CH3 to C to double bond O still to an oxygen with extra electrons, right? So if it has an extra electron, you know it's negative. And then plus, there's another atom, isn't there? It's hydrogen with a plus on it. That's why you have this writing down here. So that's what happened. It broke off, it dissociated. Now these are ions. This is an ion here, right? This whole thing, it's a molecule, but it's an ion, isn't it? It's a polyatomic ion. And then this here is an ion as well, isn't it? And this is a hydrogen atom, a proton, because hydrogen only has 1 electron, and 1 proton releases most of the forms of hydrogen. So as 1 proton is floating around, it has a positive charge, where this other one has a negative charge, right? So this is a negative, this is a positive. If you have negatives and positives in aqueous solution in water, then you know this can conduct electricity. But notice it conducts less electricity than the previous example. That's because it was 100. If you had the same mass of solute dissolved in water, then the other one had 100% dissociation, and in this one you only had 50% dissociation. So only 50% of the molecules can help conduct electricity, so you have less conductive ability, because remember, the water itself is actually a non-conductor, right? Or it doesn't conduct electricity well at all. So that explains why this is slightly conductive. All right, let's go to the next one. Now sugar is a C6H12O6, right? So C6H12O6. And it turns out that sugar does not ionize in water. It's still soluble because it's polar, but it's not ionized, so there's no negative or positive charge, all right? So because there's no negative or positive charge, and the water itself doesn't conduct electricity, then this solution of sugar and water, if it's pure water and just pure water as a solvent and sugar as the solute, there would be no conductivity. All right, let's find. Now this graph is pretty simple. These two are where really you have to focus your energy on. This one will come into play, and we're going to look at the solubility curves in a minute. when you're talking about solubility, how soluble is something in water? Well, you have to consider that most solids, as you increase temperatures, two things are going to impact the solids dissolving in water. How much you stir it, how much three things. How much you stir it, how much kinetic energy is available for these things to come into contact, to come and meet each other. The water molecule coming into contact with the solid. Then the next thing is temperature. The faster they're moving around, the more often they come into contact with each other. And the last thing is surface area. So if you have a cube, right? If you have a cube and you put it in water, then the water can only come into contact with the sides of the cube, right? And that's the only place the water molecules can come and hydrate or solvate the sugar into the water. Now, if you crush that, so it's just a powder, so these tiny little particles in a spoon, right? So if you have the spoon now, or you have the sugar and you put that in water, then this is broken up. So now all the water can come in and fill in all the little nooks and crannies and take the particles and break it up and put it right into solution. So the time it takes for this to become soluble is improved if you can crush it up. So you can improve solubility if you crush the material up rather than having a block of it. So knowing that those three things, we'll look at it in just a second as well, are the kind of the variables that you have to consider when you're asking yourself, is something soluble in this, is a solid soluble specifically in water. So temperature is a big deal, and the warmer it is for most solids, the more soluble it becomes. That's a trend. This is not a specific solid. We'll look at specific solids in just a minute, in a few minutes. With gases, it's pretty clear. If you're just keeping everything the same pressure, the temperature is the big. As you increase temperature, you decrease. The relationship is opposite that of solids. As you increase temperature, you decrease solubility. So things come out of solution as you increase the temperature. So gases and solids have opposite relationships. Now, there's all kinds of laws, and I initially was ambitious and I wanted to describe those laws to you, but the slides, have deleted them, and so focus on the slides that we're talking about here, okay? So some solids are exothermic. That means that they release energy as you increase. And by the way, if we look at endothermic, remember endo means in, right? So endo means in, and exo means out, and thermic means heat. And so this one is this solid. These solids are taking energy in, and as more energy you put into them, the more they hydrate, right? So endothermic hydration means the more energy you add to it, the more it's going to dissolve, the more it's going to go into solution. When you look at exothermic, on the other hand, it's opposite, right? So it's releasing energy when it becomes hydrated. So the hotter it is, the less soluble the material becomes, and the less heat that you put into it, the more soluble it becomes. All right, so these are some important prefixes, and these are three important relationships you have to know by Thursday. So here you have water dissolving a salt, and in the PowerPoint, you saw it was kind of an action little GIF, but here you have these molecules, they're vibrating, and you see that in the PowerPoint, and as you're looking at it, you see that in the PowerPoint, and as you're looking at these water molecules vibrate, there's kind of three relationships that you see developing really quickly. And the first one is that the relationship between these two molecules. Now, one molecule of oxygen, water, as we described earlier, is called a dipole. So it means one side's positive and the other side's negative. It's called a dipole. If two of these things, this water and this water, are interacting, they're pulling on each other or pushing on each other, right? this pushing and pulling is called a dipole-dipole interaction. Two things with dipoles, pulling or pushing. That's the relationship that's happening between the water molecules. That's that cohesion we were talking about earlier. Okay, so now we know that these water molecules don't just pull on each other. They also go in and start pulling on the ions. These are ions, right? There's an ion and there's an ion here. This gray one and this green one. So we look at this ion, and this goes back to the quiz question that you've gotten twice, and some of you have not done well on either attempt. So pay attention. The logic is simple. You just have to put together what you already know. You know the components, but you haven't been able to put together the solution. So this water molecule, the oxygen, as you see here, is negative. Remember, this was an emoji for the positive side, and then moving over here towards that's right, the negative side. So this is negative and this is positive. And we spent a lot of time describing why. You need to go back and look at your notes or the videos or the book and explain, or go back and look at those explanations as to why this is positive and this is negative, if you're interested or confused. So this is negative, and therefore, by definition, the other side is positive, just like the emoji. And they're pointing towards each other. They're all pointing towards each other. And just like you saw earlier on in the answer to the quiz question, just like you saw before that, the answers to the quiz questions on Friday that you've gotten repeatedly, that we covered in class repeatedly. If this is negative and it's pointing towards this gray molecule or atom or whatever it is, this variable, if this is negative and it's pointing towards it, they're all surrounding it with this side pointing towards it, and this side's negative. We just identified that. So then this negative side is pointing towards this little gray thing, and it's partially negative, right? I mean, we understand that. I hope you understand that. It's partially negative. And so that's why we put that little symbol, that little delta, lowercase delta, these are all negatives here, partially negative charges. They're all pointing towards this little gray dot. So what's happening here? They're pointing towards it. Are they being repelled? I don't think so. If they were being repelled, what would happen? They'd move away, wouldn't they? So they're pointing towards it. So that means that the gray thing, that gray little variable, really, if you think about it, has to be a positive, right? So the gray thing has to be a positive. That's why it's pulling towards it. The negative is going to point towards the positive. Opposite charges attract. So this is just simply an application of something that you've known since you were probably 5. Opposite charges attract. The negative and positive ends of a magnet attract each other. So now here you have here's these little ears, right? And we know they're positive. You look at our emoji, you know they're positive. So you know that this side is partially positive. I'm not going to put the second positive. We understand that. This side's partially positive. This side's partially positive. This is partially positive. So the partially positive side is pointing towards this green thing in the center. This green thing in the center. So these partially positive sides are pointing towards this green thing in the center. So what is it that you think is going to happen? What do you think the consequence of that is? What does that mean that the positive side is pointing towards the center? If we remember that these things are pointing, therefore they're probably attracted to, right? Assuming it's not some kind of random event. It's not, obviously. They must be attracted to that green thing, and they're positive, and we know opposite charges attract. Then you should understand that this green thing in the center is negative. Since the little positives are pointing towards it, the opposites attract. So this is negative, and then this is positive. And that should be pretty clear by now, I hope. Okay. Let's see if I can. All right. So, negative and positive. And indeed, if you look here, it's negative and positive. That was the key. So you can tell what the charge of the ion is in the solution depending on which side. And remember, I told you, if this is a picture of Mickey Mouse, right? Then the ears are positive and the face is negative, right? We talked about that. So that when you look at this, you should see negative here and positive here, right? You should see that. It has to be in your mind. All right, so that's overcoming attractive forces between the solid. So the solid had attractive force, the negative and the positive were attracting each other, but water came in and got in between them and separated them. All right, so when we're talking about this kind of interaction, it's overcoming the attractive forces of this molecule. It's not a molecule of this solid. It's a compound. It's an ionic compound. All right, so let's take a look at the next slide. So for this, so again, what are these things called? Well, the interaction between the water molecules again are dipole. Why? Because this has a dipole, one positive, one negative, two poles, right? North and south pole, positive and negative pole of a magnet, positive and negative pole of this molecule. So this has a dipole. So the attraction between the water molecules is called a dipole. The attraction between the water molecule and this ion, and these are ions, right? This attraction between these two, the water molecule and the ion, is called the dipole because the water is a dipole. And what's this? An ion. So we call it ion-dipole interaction. And we're talking about salt. We're talking about an ion-ion interaction. So you have a negative and a positive, negative and a positive. All right, let's move on. All right. Now remember, in the PowerPoint, this is a lot of slides put together, right? This just gives you the whole. This is probably like 5 slides. So that's why there's so many fewer slides in the movie than there are in the PowerPoint. So how do I get sugar to dissolve faster in my iced tea? 3 things that we talked about when we're talking about how fast things dissolve in water, right? We said there's stirring. This is what? Get the fresh water attracted to and bond and interacting with the solid. And so we want fresh solvent that's not interacting with any solid to come into contact with this material. And in the previous example, I said, if you had a cube, right, then the only way the water, if you stir it, you have this rod that comes in and stirs it, then it's going to be moving in all directions. The water is going to come into contact, and it's going to get pushed out of the way, and there's more water over here. So as you stir it, all this fresh water comes in and comes into contact with this cube, dissolving it, the new water dissolving, taking away more and more of this solid until it disappears. It disappears. It did not destroy it. So when we're talking about this, the solution, you have to, and how do we get it to dissolve faster? We have to think along the lines of increasing this, how much solvent comes into contact with the solute, right? And to that effect, you're going to have to look at, the greater surface area. So if we took that sugar cube and we, which is going to be faster, the water trying to get in all the sides of the cubes, or if we crush it, right, and we put it in a teaspoon, and it's this powdered form, crushed up, ground up, and we take that powder form and then we dump it into the water, which is going to dissolve faster. What's going to be the one that you grind, right? So the ground sugar or powdered sugar is going to come into contact more quickly with the water. So the solute-solvent interaction happens faster because it's broken up. So here we're dealing with surface area. The area of the surface is increased when we break it up into tiny pieces. Then you add sugar and you can add it to the warm tea. So again, temperature. Remember, the warmer the temperature, the higher the temperature, the faster things dissolve for most solids. We went through that just a few slides ago. So faster rate of dissolution in higher temperature. That's normal, and there are some solids that don't do that, but sugar's not one of them. It's a normal solid, meaning it's an average solid. Okay. So what is a solution? So let's think about some terms, some vocabulary words that we've discussed. There's solute, right? That's the stuff that's getting dissolved. It's usually in less concentration. And then there's solvent, the stuff that does the dissolving, usually in greater concentration. So in the answer, the solute is the substance that gets dissolved, right? The solvent does the dissolving, right? So it's pretty simple. So here we have soluble and insoluble. Well, remember the prefix in means not, right? Not. Soluble means it goes into solution. Insoluble means it doesn't go into solution, at least not easily. So it's soluble, can be dissolved. A substance that is soluble can be dissolved. Insoluble means not being able to be dissolved. Miscible and immiscible. Now, immiscible and miscible is just dealing with liquids. So immiscible substances are liquids, right, that will dissolve each other. So in the case of water, it's a liquid, and ethanol is an alcohol that's a liquid. And when they enter and mix with each other, they're 100% miscible, which means they mix in completely in this new solution. They dissolve each other. So miscible is a very interesting term. We just talked about two liquids dissolving each other, right? So when we're talking about solutes and solvents, we're talking about dissolution, right? Is something soluble? If we're talking about two liquids, we're asking, is something miscible? So soluble is for solids, and miscible is and soluble is also for gases, but miscible is for liquids, right? Electrolytes and non-electrolytes. So either it has electrolytes and the stuff conducts electricity, or it doesn't have electrolytes and it doesn't conduct electricity. So electrolytes, when water is a solvent, remember, most of the time water is a solvent. If you have things that are ionic, they conduct electricity. If there's no ions in here, there's no conduction of electricity. So when talking about electrolytes, do they conduct electricity? All right, moving on. Types of solutions. In gaseous solutions, we talked about the idea that air is the perfect example of gas. So you should know that a solution of gas. Air is made of nitrogen gas. Air is made of oxygen gas. Air is made of carbon dioxide gas, right? So there's all kinds of other gases, smaller quantities, but those are the three big ones. And air is this big mixture of gases, homogeneous mixture, so it's a solution of gases. Liquid solutions, well, we know what they are. Water is one, and there's this word that we've learned that has to do with how water, what we call it when water is the solvent. We say it's aqueous. All right, so if something's aqueous, if it's an aqueous solution, it's a solution where water is a solvent. Solid solutions, you have more than one solid that's homogeneous. Now take a look at this. It's homogeneous. You can't tell the difference between one part of it and another. It looks like one kind of thing. It's a filling, obviously. But there's more than one metal in here. It's not pure silver. It's not pure gold. There's a bunch of different metals. There are a couple metals in here. And they're dissolved in one another. They're one thing now. They're homogeneous. But they're solid. They're solid at room temperature. So this mixture, this homogeneous mixture of solids, is known as an alloy. All right. So an alloy is a homogeneous mixture of a solid. So obviously, when we melt them, we mix them together, and then we let them turn into a solid, and we call those alloys. So steel is an alloy. Stainless steel is an alloy. Bronze is an alloy. Bronze is not a metal. It is a metal, but it's a mixture of metals. It's called an alloy. All right, let's move on. Making a solution. Solute, solvent, particles are separated. So in the solute and the solvent, the particles are separated. So the solvent separates the particles. The solvent particles are attracted to the solute particles. In fact, they separate them from each other. The solvent separates the solute particles from each other, and they go into solution. Water is called, when we're talking about hydration, we're talking about water. All right. So this solvation, the whole thing's called solvation, right? Anytime you create a solvent dissolves a solute, we call it solvation. But when we're talking about water being that, we call it hydration. So when you say hydrate, 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 you're talking about add water, add solvent, because there's plenty of solutes that need to be dissolved. Now this is a big one. This is a big one that's going to drive, and the only reason we went through all of that was to understand like dissolves like. This is the key idea. I can tell you you're definitely going to have questions on this in the exam. So like dissolves like. Like dissolves like. It's a key idea. So interestingly, so what this means is that polar substances more easily dissolve polar substances than they do non-polar substances. It gets a little tricky with some of these, and I didn't really want to discuss it, but I can't seem to find a way not to discuss this. There's some exceptions to these, and to the idea that polar dissolves polar and non-polar dissolves non-polar. So we're talking about here this idea of like dissolves like. So when we say like, we mean all things polar and all things non-polar. They dissolve each other, right? So we're talking about these things dissolving each other. So will methanol, for instance, be dissolved in water? Sure. But will oil be dissolved in water? No. Now, when we look at these molecules, though, things get a little tricky. So water is almost easy. Water is a polar molecule. It's not going to really dissolve nonpolar substances. When we say not going to dissolve, we're talking about it's highly insoluble, right? So these things are highly insoluble. These nonpolar things are highly insoluble in water. But does that mean that no molecule of this material is going to go into water? No. Rarely do we say 100% not going to do it. Methanol. Methanol happens to have there's 3 H's on it, just like the molecule before. And then it has an O and an H. Well, this thing here is polar. But this thing over here is nonpolar. So the polar part will dissolve polar materials. That's fine. But then it turns out that the nonpolar part will dissolve these nonpolar substances to some extent. So it's possible that this polar molecule, it's polar, but also has a nonpolar side. So you have like this division, if you will, of the two sides of the molecule. Now this is a very important idea because that's actually going to drive a lot of our discussion about the cell membrane. So you have to really get this idea in your head. You have this side that's polar, right, and this side that's nonpolar. All right. So it's able to, and this, because it's so small, and the polar side's so close to the nonpolar side, it's not a very good nonpolar solvent, but it does an okay job. Well, it does a poor job, actually, but it's used as a solvent for some situations. So interestingly, the polar molecule here, the polar nonpolar materials, when we're talking about ethanol, is we said methanol had this OH group on this carbon, right? So this tiny little carbon that had an OH group on it, and it had this property that you have two sides of the molecule, a polar end and a nonpolar end. So we said these two are so close together. I'm not going to put the other hydrogens there. We say these two are so close together that it's not a very good polar solvent, a nonpolar solvent, but it's still good. It still is a polar solvent. Ethanol has, instead of one, it has two carbons connected to it. Again, I'm not going to put the H's for the hydrogens, if you don't mind, and except for the last one. And what we see here is that you have this side that's polar. This is definitely polar, but then your nonpolar is much longer, much bigger. The molecules are slightly bigger, actually slightly bigger. So again, ethanol can dissolve both polar and nonpolar stuff. So if, let's say, permanent marker, let's use that as our example of nonpolar material. So ethanol can actually dissolve polar, a molecule like permanent marker, the stuff that makes up a permanent marker. Acetic acid is polar. Probably does a decent. It can probably dissolve some slightly nonpolar material. Acetone we know is a good nonpolar solvent because it's nail polish remover, and nail polish is definitely nonpolar, right? And it does dissolve nail polish very well. In fact, it's sold that way. So acetone is one of those things that has a longer molecule. It has a polar side and nonpolar side. Ionic compounds just won't mix with nonpolar compounds, and that's all there is to that, for the most part, right? So I don't work in absolutes because there's generally an exception, and you can always change things. In science we like to cheat. We like to use technology. We could always change the rule. So ionic compounds they're just not going to mix with nonpolar substances. Now, carbon tetrachloride, very, very nonpolar. Toluene is paint thinner, so you have paint. Could you use this? You could use these. Now, this is very dangerous. It's a carcinogen. It goes into gas at very low temperature, so it's not something you want. And paint thinner is also dangerous, and it goes into flammable, and it goes into the air very quickly as well. And so when you're talking about paint thinner, if you want to remove permanent marker, paint thinner would work really well. These are gasolines, right? Octane, heptane, hexane, or at least they're components of gasoline. And we have here benzene, very good nonpolar substance, and oil. So all these will dissolve other nonpolar materials, but polar materials don't really mix well with them. Will some of these dissolve some of these? Will some of these dissolve some of these? Sure. For instance, acetone, because it has the same idea as ethanol and methanol, the polar side, the nonpolar side. But the things that are polar, like water or things like ionic compounds, just won't mix with these at all. So the bottom line for the rule of thumb, and what you're going to have to worry about in the test, and again, this stuff is going to become very important next week, But in the case of this exam, what you have to remember is like dissolves like. It's just that simple. All right, let's go on. I said it's just that simple. Just remember, if it's polar, it's dissolved by a polar molecule. If it's nonpolar, it's dissolved by nonpolar. And some molecules can dissolve some nonpolars. Some polar molecules dissolve some nonpolars because they have one side that's nonpolar, the other side that is polar. So what is the solution? Dissolving ionic compounds in water. Water is polar because it has two oppositely. And it says the answer is charged, but really, remember, please, it's partially charged, right? Partially charged ends, right? So this is partially negative, and this is partially positive. So let's not forget that moving forward. This killed you guys on two quizzes now. This idea that this molecule has this partial negative charge and this partial positive charge. You got to know that. I've been hammering it in your head in many different ways, but you're just not getting it. I don't know why. You have to understand these are partial. This side is partially positive, and this part is partially negative. This is going to point towards anything that's positive. This is going to point towards anything that's negative. And that's how. And also, this is the reason why this polar molecule can dissolve salts in other polar molecules. Like dissolves like. Anything with a charge or like even a partial charge, they dissolve each other. Things without a charge, they dissolve each other. All right. So the blank end of water is attracted to the anion. Now remembering that I said you don't have to really, I'm not asking you to remember that an anion is a negative ion. You should, because it's in chemistry, you're going to need it next year, but I wouldn't really worry about it this year. But know that a negative ion, anything with a negative charge, is going to be attracted to what end of the water? Negative charge will be attracted to what end of the water? Opposite charges attract. So negative charge is going to be attracted to the positive charge. And what is the positive charge in water? The hydrogen. Right? Okay. Moving on. So we're talking about combining dissolving ionic compounds in water. We've already gone over it. This is just one more example. These things are attracting one another. The negative and the positive are attracting one another here strongly. We put it in water, and then all these molecules, these millions of molecules come in, and they're pulling and pulling and pulling. Well, they pop. They remove. They're removed. They become disassociated, right? Dissociated. And what happens? You get a pull from all these different water molecules, end up overcoming the pull between these two ions. So the ionic compound is dissociated into individual forms. So when you're looking at an ionic compound, they separate in a positive and a negative. Now we just covered all this, but yet again, I'm just giving you different ways of looking at it, right? Ionic compounds is dissociated into individual ions. So you have an Na plus and a Cl minus. That's why the water becomes conductive. All right. So it used to be NaCl solid, salt cube, right? Crystal. Put it in water, and it dissolves into Na plus and Cl minus as water hydrates it. As water dissolving molecular compounds in H2O. That's a little more. It's one addition to what we've already discussed. Not a great big deal. When water dissolves something, when something gets into solution with water, if it's going to do it well, it has to have at least one part of it be charged. So here you have this OH, like I just drew 4 times for you. The O, oxygen, is negative. The H is positive, partially positive, so it's polar. So this end here, this would be ethanol, right? 2 carbons, right? So 6 hydrogens, and this is an OH group, so this is ethanol. I just drew it for you earlier. This OH group is polar, so water is able to grab onto that and keep this ethanol well mixed. So water has this capability, because it's so polar, and there's so many of those molecules just floating around and moving over each other, that they're able to take this molecular compound that is slightly polar, that is polar. It's a molecule. It doesn't separate them like NaCl. Remember we just said Na is separated from Cl. That's because it's an ionic compound. This is a molecular compound. These bonds, remember, 20 times stronger than the attraction between hydrogen and oxygen in hydrogen bonds. 20 times stronger. So these are not going to break as water comes around and pulls the molecule in. So it just pulls everything in with it. So solute is surrounded by the water molecules just like in NaCl, but the difference is this is not going to break up. The solute remains intact. All right? That's the difference between molecular compounds being dissolved and ions being dissolved. How do we speed up solvation? Well, I mean, this is the third time we've said it. Stir and shake it. Break apart the solute. Break apart the solute. Heat the solvent. So those are your three. Increase surface area. Increase the solute contact with the solvent, or solvent contact with the solute. And increase the heat. As you increase heat, you increase the solvent going into solution. All right, is it soluble or not? That's the question. Any specific content. So not all ionic compounds dissolve in water. It's weird, huh? They said like dissolves like. I said water can dissolve ions, but then not all of them are able to be dissolved in water. So there's those exceptions again. So we have these solubility tables. And insoluble, S for, equals S for solid, so it's solid, it's insoluble, and it's not always, but in this case for what we're talking about. And soluble equals aqueous. So if you say solid in a chemical equation, that means it's not in solution. If it says aqueous, AQ, it is in solution. All right, so let's. And then there's these things that are called solubility rules. So let's take a look at some just superficial concepts for insoluble and soluble. In reality, ionic compounds all dissolve in varying degrees, and I mentioned that earlier. So when we talk about insoluble, it's really, we use the word insoluble, we just mean it doesn't go into solution very well. It takes a long time for the stuff to dissolve. All right. So because it takes so long, that it's basically insoluble for some of these. All right. Solubility depends on a lot of things, but the solubility curves we take a look at temperature. Remember, temperatures are a big deal when it comes to when we're talking about solids going into solution, and gases as well, but especially ions. So it turns out some of these solids, and this looks kind of crazy, the curves look crazy, but if you take a look at them, some of these, like potassium iodide, that's a salt, it's actually very soluble, about 128 grams per gram of 100 grams of water goes easily into solution at even 0 degrees. Even at when water is a solid, potassium iodide goes into solution. So it's very, very soluble in water, and all the way up to something like 30 degrees, where you have some crazy amount soluble in water. So here you have sodium nitrate. Now this stuff starts off, it's about 75 degrees. You're about 75 grams of this stuff is soluble in water at 0 degrees, right? So so sodium nitrate will dissolve in even solid water. All of these will dissolve in ice to varying degrees. This one here, potassium chlorate, is slightly soluble as compared to potassium iodide, right? So this one, somebody might say, is insoluble, right, at 0 degrees, and this at 0 degrees is soluble. So you can see the difference between insoluble and soluble. Even though it does go into solution, very little of it will go into solution at 0 degrees. But if you increase the temperature, then all of a sudden you start to see an increase in solubility. And you have to follow the right line, but you see that at 100 degrees, you're putting in 60 grams for every 100 grams of water. So 60% of that solution can be potassium chlorate at 100 degrees. And remember, this is out of 100, so the grams, this is 20%, this is 30%, right? Etc. So when we're talking about 0 degrees for the temperature, and we're talking about this molecule, ammonia, it's actually very soluble when it's cold, but as water gets warm, it's not very soluble at all. It becomes actually less soluble. Same thing with sulfur dioxide, right? It becomes much less soluble in water at high temperatures. And here, hydrochloric acid becomes less soluble at higher temperatures. At 0 degrees, hydrochloric acid is very soluble. You have up to 85 grams for every 100 grams of water. Where you come down here, and at near boiling, the hydrochloric acid you can only put what looks to be about 45 degrees, 43 degrees, 45 or 43 grams of solute into that 100 grams of water. So these curves, there's books and books of them, all kinds of databases, all done from experiments, right? So some scientists have sat around multiple times and measured how much of this stuff is going to go into water relatively quickly at these various temperatures. So this is recorded. So not all ionic compounds are dissolved in water. The solubility depends on temperature. Solubility also depends on the physical state of the material. Solubility of gas depends on pressure. So you know that every time you open a Coke can, you release the pressure, and then you see the soda bubbling up and coming as the carbon dioxide comes out of solution. Because pressure and temperature are the two big things when you're talking about gases. And that's going to be important for our discussion about oxygen and carbon dioxide being dissolved in blood. Because after all, blood is a solution. Henry's Law is something I wanted to talk about, but you know what? We don't have time. We're not going to discuss it. So let's go ahead and skip over Henry's Law. It's something you'll cover in chemistry. We don't really need to calculate it. I just wanted to have a discussion about the relationship between solubility and pressure. But it's not really that. I mean, we may come back to it if we have time to discuss it when we discuss the lungs. Because obviously in the lungs, gas is going into that solution called blood, right, is very important, right? So the changes in pressure become very important to someone. So things like iron lungs were designed to increase pressure so that we can have oxygen go into solution easier. Things like the pressure chambers for divers that are deep in the ocean coming back up, so that the gases don't all come out of solution at once, especially the nitrogen, because it's the main component of air, right? All right, so we're going to skip this one. All right, so we could calculate it because we know the formula. We know the formula S over P equals S over P. But we're not going to do it because I don't want you to stress, and we're going to go and reduce some of this. So heat of the solution, many reactions warm up when you mix substances in. So heat of solution is this idea that when you make a solution, we mix them together, some reactions will warm up while others get colder. And if you put Epsom salts in water, you'll note that the molecules, the temperature of the water will actually decrease. It'll get cooler. Where if you mix other substances into solution, the solution will get warmer. Concentration. Now this is going to be a key part of why we're doing all this solution solute business. How concentrated is something. We've talked about this already. A solution that has lots of solute per solvent is concentrated. So when we're talking about concentration, we're talking about you have this amount. Well, how do we measure this amount? We have a solvent, usually a liquid, usually water, and you have a solute, it's usually some kind of molecule or some kind of ion. If you put a lot in, like Kool-Aid, a lot of sugar, for instance, sugar is the one we've used in class a lot of sugar in there, it's concentrated, very high concentration. So a lot equals high concentration, just that simple. Where if you're talking about, if you only put a little sugar there, equals low concentration. So when we're talking about, now that sounds like it's no big deal, but I guarantee you when we start talking about osmosis and diffusion, some of you are going to be looking at me like I am speaking another language when I start talking about high and low. So when we're talking about high concentration, low concentration, as simple as that sounds, please contemplate and be able to answer questions on it. Dilute is another way of saying what? Low concentration. So a dilute liquid, a solution is something that's not so much. So it has lots of solvent, right? This has lots of solvent, and this has, so you know what, I'm going to use, if you don't mind, I'm going to use an up arrow solvent, right? Up for a lot. And in concentrate, it's up arrow what? Solute, right? So when you're mixing two, you always have a solvent and a solute if you have a solution. So a dilute solution has a lot of solvent, where a concentrated solution has a lot of solute. More solvent, it's a dilute solution. A higher concentration of solute, it's a lower, it's a concentrated solution. All right, so let's move on. A saturated solution is a solution that has a maximum amount of solute at a given temperature. Remember, the warmer it is, the more it can be dissolved, the faster it dissolves. So if you want to dissolve fast or increase how much you put into it, you can heat it up. But there's a maximum amount that water will be able to that will be able to be dissolved by water. And that maximum, when you've reached that maximum, it's called saturated. Max is maximum concentration. So this is the most you can fit into this water. It's called saturated. It's concentrated if there's a lot of solute. It's diluted if there's less solute. It's saturated if it has the maximum amount of solute. All right. Super saturated. Ooh, this is the one I wanted to do with you in lab, but we had to keep going over this stuff. It's unfortunate. But what we can do is we can take this water and we can keep putting sugar in. And what happens if you keep putting sugar in? Eventually, you get what? Sugar at the bottom. If you keep putting sugar in, it's going to hit the bottom. So what is it if it's happening? Well, it's saturated. So if I take that and I heat it up, if I take that and add heat, then this water will be able to hold more of it, and that solid that used to be here at the bottom will go into solution. But then if I cool it down again, it'll still be in solution. It just will fall out much easier. Here, where we know that solutions mean that things don't settle, and when we cool a supersaturated solution is very unstable. And when you can even just tap the side of the container, and that solute will fall out of solution. All right. So that's really basically what you need to know for concentration. We can force this because we can use it with heat, as I just explained. So, how do we measure concentration? Percentage by mass. So that's one way. We take how much mass of solute and mass of solution, and we multiply times 100, and that's how much we have. And that's it. It's just that simple. So if we have a gram of solute in 100 grams of water, because we're looking at the solubility curves, you saw it was out of 100 grams, and what would we get? We would get, this would equal about, what? 0.01, right? You multiply that times 100%, and you get 1%. Most of you could have done that in your head. You could have known 1 over 100 is 100%, is 1%. But it's always good to go over it, and if you need to review it, you should be able to handle it. It's, I think, a math that everyone's able to do based on what I've seen you do in class. So here's a really quick one, a really quick self-check. Go ahead and try to do it. Pause the video if you need to. All right, so what is the percent by mass when 40 grams of salt is added to 200 grams of water? That's 40 divided by 200. The grams cancel. And what do you get? You get, well, you can reduce it to 4 over 20. So that's 1 over 5, right? So then you get 1 over 5, which is equal to 0.20, right? Times 100, because we have to make it a percent. Percent equals 20%. So 4 over 20 is 20%. 1 over 5 is 20%. If it was 1 over 4, it'd be 25%, right? But it's 1 over 5, so it's less of a percentage. All right. So that's really just that simple, right? It's just dividing and then multiplying by 100. All right. Let's move on to the next one. So percentage by mass, and then now by volume. So we can do a percentage by volume as well. They take volume of solute, volume of solution. So when we measured mass, we use a scale, or balance rather. If you're going to use volume, you just use a graduated cylinder. You say, okay, I got 4 milliliters instead of grams, right? 4 milliliters of solute. This really helps when you're dealing with liquids, right? And you have 100 milliliters of solvent, right? So, well, how would you do that? You just take 4 milliliters and divide it by 100 milliliters. Milliliters cancel out, equals 4 over 100, which equals what? Is 0.04 times 100 equals 4%, right? So there you have 4%. We have 4 milliliters and 100 milliliters. You multiply times 100% by volume. All right, what is a percent by volume when 50 milliliters of methanol is added to 450 milliliters of water? So that's 50 milliliters divided by 450 milliliters. And you can do the math. You tell me the answer when we meet tomorrow. All right. So that was a quick and dirty concentration of solvents and solutes, and there we left some interesting and important conversations out about molality and molar relationships, and we're not going to talk about it because we just don't have time for it. But it's important. It's a concept that we should, that you hopefully by the end of your chemistry year next year you'll understand and be well versed in it. Well, that's it for solutions and solvents and solutes. We covered most of it in class. The last little bit of concentration we'll cover tomorrow in class. You have all of this video. I hope it helps. You guys requested it, so good luck to you.